Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on October 4th, 2025, about 4 days ago. The striking claim is that a single invariant, the operator norm of the output layer, controls joint optimal scaling across models and datasets, which the authors call norm transfer. The paper is titled, Optimal Scaling Needs Optimal Norm, and the implications for model training are quite significant. Beyond the invariant, the study reports atom-like scaling rules for the optimal learning rate and batch size, shows per layer group tuning can improve loss by up to 6%, spans models to 1.3 B parameters and 138 B tokens, and releases distributed Scion logs from over 2,000 runs. Also, the authors shared a GitHub repo with Disco, a distributed spectral conditioned optimizer for PyTorch. You'll find the core optimizer, param group helpers, semi-orthogonal init, and norm tracking utilities, plus a runnable example with dummy parallel DIMs. It integrates with TorchTitan, supports multiple backends and per-parameter rules, and demonstrates step time and norm tracking. Figure 1 shows that training loss hits a clear minimum at a specific output layer operator norm, and the learning rate pushes that norm higher. Panel A plots training loss against the output norm, revealing the sweet spot near 27. Panel B tracks norm growth over steps, where larger batch sizes separate the curves after a kink and then settle to a gentler slope. This behavior underpins the norm transfer idea. Well, Figure 2 shows that the best training loss occurs at a shared output layer operator norm across batch sizes. The operator norm means how strongly the layer can amplify its inputs, which acts like a dial controlling model behavior. Panel A compares data horizons and finds one batch size per horizon that lands near the same norm, while the preferred batch size grows with horizon. Panel B scales model width and depth and achieves lower loss as capacity increases, yet the loss curves still meet at the same norm. This consistency means the optimal learning rate and batch size pair must drive the output norm to that common target. So Figure 3 shows that reaching the right output norm is necessary, but it does not uniquely pick the best hyperparameters. In Panel A, many learning rate and batch size pairs hit the same target norm across horizons, which means the norm alone cannot choose the settings. Horizon means the token budget used for training. Panel B then identifies a unique best pair per horizon, and the optimal learning rate rises with batch size while falling with horizon. The fitted rule follows a line in log2 space. The slope with batch is about 0.62. The slope with horizon is about minus 0.56. So Figure 4 tests whether different layer groups prefer different learning rates. Per layer group tuning means setting separate learning rates for input, hidden, and output blocks, so each can move at its own pace. The left panel compares many settings and highlights the top 10%, and the small histogram counts which groups appear in those best runs. The right panel shows a consistent V-shape where the hidden rate is about 1/8 of the input and output. The takeaway is that a lowered hidden rate reliably improves loss, while keeping input and output higher. Alright, Table 1 shows that, for a 2-layer proxy, the best final loss appears at a learning rate near 2 to the minus 2. Depth normalized means both residual and block are scaled by depth, while complete P keeps the residual fixed and scales the block. Across initializations and residual multipliers, differences are small, which suggests learning rate transfer holds. The slight edge goes to total depth initialization with identity residual scaling. Okay, 2 takeaways stand out. The operator norm of the output layer acts as a reliable invariant for optimal scaling, and the best learning rate and batch size follow atom-like square root style rules, while per layer group tuning, with a lower hidden rate, gives extra gains. The implications are faster, cheaper, hyperparameter transfer at scale. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.